Section 9.1, Graphing Inverses of a Function. How do a graph of a function and an inverse compare? When x and y are interchanged to find a formula for the inverse, we are, in effect, reflecting or flipping the graph about the line y equals x. And here we have an example of a line. It passes the horizontal line test, so it is a one-to-one function. It will have an inverse. What does that inverse look like? There's two methods that we can use. One is just to simply take points of the given function, which in this case, this point is 1, 0, and turning that ordered pair around into a 0, 1 and plotting it. Here's another point, 2, 2. Turning that around is 2, 2. We have another point here. The coordinates would be 3, 4. Turning that around would be 4, 3. So we have these points that are already turned around. So it should continue off in that direction. And just to show you some other points, we have the point of our original function has the coordinate 0, -2. Turning that around would be, in other words, switching your x and y would make it a -2, 0. That puts it here. The point of our original function, it has the coordinate -1, -4. The inverse is interchanging or flipping those coordinates, so it would be a -4, -1. And if I extend the line to connect those, we clearly can see that they are part of that. So here is the graph of our inverse by just taking each one of our ordered pairs from the function and reversing them. The other technique, because we're reversing our x and y, is to reflect the points about the y equals x line. And the y equals x line is at this 45-degree angle. And you can see that here we have perpendicularly this point. If we reflect that about the line, we would have the point here on our original function perpendicularly to our reflection line. We have a second point. Likewise, here perpendicular, this point on our function, if we reflect it through there, we have our point on our inverse function. And we could continue on for the graph. Here we have another function. It's a cubic function. It's given by y equals x to the third power. It passes the horizontal line test. Even though it flattens out here, it's still moving along and would only, if we ran the horizontal line test, intersecting once. Because it's passing the horizontal line test is proof that this is a one-to-one function and that it does have a inverse. You have, again, two choices for graphing an inverse of a function, either point by point, and you can see here that 1, 1 is not going to change, 0, 0 is not going to change, -1, 1 is not going to change either because of them having the same x and y points on them. But if I draw that y equals x line, which is acting as our reflection line, we can reflect the points about that line. And what is curving here below will actually be curving above. What's curving above will actually be curving below. So here, if I make this a little heavier, you can see the beginning of our inverse function. We can either turn this point around as part of our original function. It would be the coordinates 2, 7, I guess it is. And we would turn that around, just make sure, 1, 2, 3, 4, 5, 6, 7, I guess it is at 8. 2, 8 would be at, and that makes sense, 2 to the third power is 8. Turning those points, switching around, would be an 8, 2. We can also see that by taking that to the y equals x line, and reflecting at that same distance gives us the point. So we have a curve here that's headed towards that point. And likewise, we have the point here of the original function, -2, -8, which turning that round would be -8, -2, or if we reflect that perpendicularly, that same distance will give the point, and connecting that is going to move away. So here we have coming into the point, hitting 0, and heading out is our inverse function of the given function y equals x to the third power.